So I am going to take out that experiment which became so popular 10 years ago. I did it in 2000, I think 11, and I'm going to take it out and see how does it look like, in what shape it is, and does it still work. Let me try it, and let me see if it is still working. This was a video that I did in 2011, and it got so many likes and so many views that basically I want to revisit it. So this is the same board that we have. This is the same coil, but you see that this coil has gone little sloppy. I mean, it's loose. I think it's because of the temperature. And this one probably has some kind of an expansion, thermal expansion, linear expansion of the metal. Something happened, but I guess there is no breakage and it should work. I still have this magnet intact. I'm glad I saved it. I did not throw it out. This is a magnet from that time, it's still there. And do I have the wires? I don't see the same wires. But no, I have the same wires from that year too. It was a yellow and white wire. So I'm going to try it with the microampere meter. You see the microampere meter is perfectly calibrated. It's exactly at the zero. Is it exactly at the zero? It's almost exactly at the zero. It's a little bit of play in there. And I'm going to try with this wire and see if it works. And some of you have given me a suggestion that you should use a stronger magnet. You should use a soft iron core into the coil. I'm going to try that and see if it works. So I'm just hooking it up. I'm disconnecting this coil with the microampere meter the way I did it 11 years before, and see if it still works, right? So let us see, and let me settle down. Oh yes, look at this. It still is working. So there is no breakage, there is nothing, it's working still the same. So somebody commented that you have to do it in one stroke, like this way, because of the opposite polarity. It's like kind of canceling, but it looks like that if I do it one stroke, it doesn't work. So one suggestion was that use a stronger magnet. What if I change the wire? Like this wire, I think is good, still good, but I think it's very thin. Because of the thickness of the wire, I think the resistance of this wire must be much larger. So I have these two another wires, like this is this one is thicker wire, so I'm sure it has a less resistance, so maybe it will create more effect. So I'm going to connect it to this. Oh, let me do it this way. Is it connected? Yes. I could have done it. And see if there is any change into this if I do with this wire. Oh, my apologies. Look at this. No, not really. Not much of a difference. It's almost the same. So it's still going to one. Let's use a stronger magnet. So what I have is these three magnets. I got it, somebody gave it to me. These are like medical magnets that from the cording, and then very, very powerful. I gotta be very careful, otherwise it's gonna smash my finger. So I'm going to use this and see if this one works with it. Yeah, it works. That definitely works. It is very clear. I'm going to see if I use all of them, is the deflection going to be more? Wow, this is so powerful. I cannot bring it. I cannot. It's like so powerful. Yeah, I see a bigger deflection, right? I did see a bigger deflection with this powerful magnet. So definitely, if the magnet is stronger, ooh, let me connect this one too with it and see if it will work even better. It's a very clear deflection now I see in that one, right? The deflection is much bigger. Okay, one direction. So what is happening basically, this magnet has a magnetic field, magnetic lines of force. And when I'm moving through this coil, when I'm moving over this, the magnetic field which this one is generating is passing actually through this, and that magnetic field actually is changing. So magnetic field means magnetic flux. So the flux which is associated with this coil is changing, and whenever there is a change in the magnetic flux, an EMF will be generated. And EMF when generates, because it's a closed circuit, then what happens in that situation, the current will flow, and that will be called induced current. So an EMF will be induced, in turn it induces a current, and that is why you can see that deflection. Somebody very recently advised that use a small bulb. Maybe that's a very good idea. If I connect a small bulb and the bulb lights up, that will be fantastic. I'm going to try that one as the next one and next improvement. Somebody also mentioned that if you put a soft iron core between this magnet, then it in this coil, then probably the more flux will be associated, and it might do a better job. So I do not have any soft iron core, but I do have these pins. I'm not sure if this is totally a ferromagnetic substance, or if this is totally an alloy, but there's no harm in trying because it does get attracted by the magnet. So there is definitely some magnetic property into it. So what I'm going to do, I'm going to just insert a soft iron core. I mean, it's not soft, but let's try it. There's no harm in trying it. I'm going to insert it into this and see how it works. Oh, this is a challenge. Yes, let's see that if it, oh, it's got inside. I'm going to use the whole magnet, the whole thing, and see if the deflection gets better. The deflection did not get very better, but what is that this started vibrating because this pin gets attracted to the magnet. Maybe what I can do is I can also try, somebody suggested if there is a small division ampere meter. So I have this milliampere meter, which I have not used also from a very, very long time. I am going to try to use it and see if it shows some deflection. So not the 500 milli, maybe 50 milliampere, right? Let's see if it shows any kind of deflection with this. The needle is moving a little bit. I don't see much movement in the needle because it looks like that it is not perfectly calibrated also. Can I calibrate it? I don't know, but I can try to fix it for a second and then see if this can work a little better. Yeah, and then I will calibrate this one a little bit too. This one is, this is perfect. This looks better. Let's see if it works. Now, any deflection? Yes, it shows a very minimal deflection. I wonder if this deflection is strong enough, if this current is strong enough to light a very small bulb. I mean, there's no harm in trying. I can try it some other time. So what is happening again, the flux which is associated with this coil is changing. So I have a bar magnet somewhere. I should have a bar magnet in this. I can get it from my closet, a bar magnet. I have a lot of bar magnets. Whole bunch of bar magnets, and I can do some. Yes, one day I'm going to show you guys my closet, and a lot of stuff in the closet that some of them I'm not using. I'm planning to give it away to whoever needs it. So this is a bar magnet, this is North Pole and this is the South Pole, right? So when you have a bar magnet, the image that you get in the bar magnet is something like, the internet is not that great today. Let me just open up a new page. So the bar magnet, the magnetic field of this is the North Pole and this is the South. This is North and this is South. The magnetic field, the lines of force looks like going from North and it goes into the South, outside the bar magnet. And inside the bar magnet, it goes from South to North. These are closed curves. The magnetic lines of force, they never cross each other. The reason why they don't cross each other, let's say this is the second line, if it crosses each other and I want to find out the direction of the magnetic field at this point, then I have to draw a tangent. So basically I have to draw two tangents saying that there are two directions of the magnetic field at the same point, which is not possible. So that's why the magnetic line support never crosses each other. So if I put a coil in front of it, and the lines that are passing through this, that is the magnetic flux which is associated with this coil, right? So if I have this magnet here, let's say in this position, and this is the lines I'm saying it's a powerful magnet, and these are the straight lines like this. And then they're going like so, and I have a coil here. Let's say this is the plane of the coil. The area of this coil is, let's say, A. So what is the flux associated with the coil? That flux is given by the symbol phi, and the flux associated with this coil actually is B times A. What is B? The magnetic field, the magnetic flux, and the flux which is because of this magnet, and A is the area of this coil. Now, if this is perpendicular to it, so the normal to this is in the same direction, so the angle theta is equal to 0 degree. So phi will be BA only, that will be the maximum value. But if this coil is like changed, like it has a certain, it's inclined at a certain angle. So right now this is the position. So this is the magnetic magnet and this is the coil in front of it. So this is the direction of the magnetic field. These are how the lines are going, and the normal to this plane, or you can say perpendicular to this plane, is in the same direction as this one. So the angle between this and the direction of the magnetic field is 0. So the flux is maximum. What if I turn it a little bit? What if if it's like inclined this way or this way? Then I have to take the component of the magnetic field in that direction. So in that situation, the value of the flux phi will be the component P cosine theta times A. So flux, basically the general formula of flux associated with the coil is BA cosine theta, which basically is nothing but a dot product of B and A. Now, if I do this plane like this, then this normal is perpendicular. This is making an angle of 90 degrees. So now the value of theta is 90 degrees. So if the value of theta is 90 degrees, then phi is equal to BA cosine of theta. If theta is 90 degrees, this is 0, so the value of phi will be minimum, and that will be 0. So in this situation, the flux associated with this coil is maximum because most number of lines of force will pass through. In this situation, the flux associated with the coil will be minimum because no lines of force will pass through this. So no flux associated in this situation, maximum flux associated in this situation. So this has a flux, this magnet has flux. This has magnet lines. How it is associated, I don't know. But it is when I move it, it changes. And that's what Faraday said. Whenever there is a change in the flux associated with the coil, then what happens in that situation? The EMF is generated, and that's called induced EMF. And if the circuit is closed, it is called an induced current. It generates an induced current. And that induced current we just saw with the help of a microampere meter or milliampere meter. So it still works. That's wonderful. I'm going to try next one with the small bulb. I'm going to try to find out a little bulb and see if I can get smaller, less resistance wire, and see if we can light up the bulb, or maybe I can make some changes into the construction of this one and make a new coil by taking longer wire even, or a bigger bore. I will try that. I'll just keep making modifications to that. looking forward to more modification to this experiment. Thank you very much.